In this video, we're going to be having a look at circular motion again, but this time, initially, we're going to concentrate on how the centripetal force acts on different objects. And the example we're going to focus on is actually a Ferris wheel going around. And also, later on in the lesson, we're going to be having a look at an example, an examination question on circular motion. So the first thing then, a Ferris wheel is one of those rides you get at in the in any sort of theme park, and it basically just goes round and round. So inside here, so if this ride is going round and round, you basically have you can be at 4 different positions on here. You can be on the 12 o'clock position over here, you can be on the 3 o'clock position, the 6 o'clock position, and the 9 o'clock position. So there's 4 different positions and we're going to analyse all the forces on the Ferris wheel at this point onwards. So the first thing I'm going to say is, let's just say the Ferris wheel is going around this way with a angular velocity omega, and every single time there is a mass acting inside this capsule. So the capsule's own mass is causing it to have some weight. So we're going to say mg is pointing downwards in every single one, because mass is always acting downwards. So that stays the same. The size of this arrow should also stay the same in this case. In this first, the 6 o'clock position over here, what we have is the support force going upwards, so it's balancing out the mg. So we've got an S force which is pointing towards the center of the circle. In this one, it's exactly the same. The support force is basically balancing out mg, and in this one it's exactly the same. Support force balancing out mg. In this case, there is a special case over here, because it's going around. The support force itself is actually pointing in the downwards direction. So support force is acting downwards. So let's just put this arrow over here to show that it's pointing downwards. And what we have is, so over here this force is acting towards the center, but over here there must be another force acting towards the center of the circle, which is causing the centripetal force. So in this case it is the frictional force, so F, and in this case it's exactly the same, so F. And what we're going to do is we're going to analyze every single position now. So position number 1, the 12 p.m. position, which is right at the top over here, we've got 2 forces acting together, mg and s, providing the centripetal force. And if you remember from last lesson, centripetal force is given by mv squared over r. So in our case, it's s plus mg is equal to mv squared over r. In the 6 o'clock position, it's only the s towards the center of the circle. So essentially we've got s take away mg, because this is acting in the opposite direction, and that's equal to mv squared over r. And in the 3 o'clock position and the 9 o'clock position, we've just got ff, so 3 p.m. plus the 9 p.m. position. We've got 2 forces, we've got ff is equal to mv squared over r. So there is the Ferris wheel all done for us. Let's just say you were going over a hill on a long drive somewhere, over a country lane. So if that's your car going over a hill, and you approach it with a speed v, coming in like this, this hill over here has got a radius r. So that's the midpoint of the circle, so it's got a radius r, and therefore we can work out the centripetal force in this case as well. So again, there's different forces acting on here. So the first force, the easiest force to actually label on, is the mg. So that's the weight of the vehicle, and we've got a force balancing that out, which is s. So s, support force, should be the same size arrow, but I haven't got enough space there to show it, but s and mg balance it out. So the centripetal force to go around this hill with a radius r is going to be mg this time, which is pointing towards the circle. That must be larger than s, and that must be equal to mv squared over r. And we can say here, when you lose, when you do airtime, so when you do any airtime on this type of hill, you lose the s automatically, and you've only got mg. So in that case, mg is equal to mv squared over r. So you can calculate VO, and VO is basically the maximum speed you can do without actually without actually doing any airtime on this hill, and that's how they actually calculate maximum speeds over hills.